Hello everyone. In today's video, I wanted to introduce you to a web app that allows you to explore analysis of variance, or ANOVA as it's called. Sometimes the intuition behind ANOVA and how we're using it to compare means is a little bit lost on intro stat students. They hear the name variance and they think we're comparing variances. They don't hear anything about means in that title. And so this tool allows you to really dig into that and demonstrate how those variances are being used to illuminate comparisons among means. On the left-hand side of this web app is a configuration tab that allows you to specify how many groups you want to compare, how many samples in each of those groups, what the common variance is going to be for them, and then ultimately what you want those means to be for each of those groups. Each of these is configurable, so you can add more groups or fewer. You can add samples. You can change this variance to be something larger or smaller as you'd like. And then you can see that by default, the groups are given increasing means, and you can change that however you'd like. But in the background, what's happening is that mean and the common variance is being used to generate the samples of size n from a normal distribution for each group. So the sample means are not going to be exactly equal to what you've specified there because it depends on the random variates that are generated. But those are the means that are being used in the background for that normal distribution. This scatter plot is interactive. It allows you to click on a point and it will highlight some deviations for you. For example, this point that I clicked on shows me in purple the total deviation between that observation and the grand mean. There are also red and green lines that break up that purple line into the deviation of the observation to its group mean, as the green line would represent, and then the red line represents the deviation from the group mean to the overall mean. And so you can see visually how that purple line is made up of the green line plus the red line. And by clicking on these data points, it will show you the purple line, the total deviation, and the red line, the deviation between groups, and the green line, the deviation within a group. And one of the fun things you can do here is to animate the partitioning of those deviations. So first it will show you the deviation of every observation to the grand mean. So essentially, this is like the numerator of a sample variance if we had one sample. The sums of squares then will just be adding all of those together. It calculates that. Next, it splits those purple lines into the red and green lines. And this is very helpful to see the different sources of variability as well, because the green lines show the deviation from each observation to the sample mean, and the red lines show the deviation from the sample mean to the overall mean. And students will start to notice that red line is going to be the same for each observation within a group because the group has a single mean, and it will be the distance between that mean and the grand mean. The green lines, however, will be different depending on where the sample mean is and where the observation is. So the animation then will calculate the between sums of squares, squaring all of the red lines and adding them up, and then doing the same thing for the green lines. And you can see here that the total sum of squares then breaks out into the sum of squares between the red lines and the sum of squares within the green lines. This sets the student up for the formulas that come below all of that in the next section. And hopefully with that animation and being able to see those different lines, these equations will make a little more sense, where the total sum of squares is really just a collection of all of the deviations of the observations from the overall mean squared, and then we're summing them up within a group and then across all of those groups. Similarly, the between sums of squares becomes a little more intuitive now because all of those red lines within a group were the same distance, right? So the sample mean to the overall mean, that's going to be the same for every observation in that particular group. Those deviations are going to get squared. I multiply them by nj because I have n of those same deviations. And that hopefully makes a little more sense to the students now where that equation is coming from. And then the within group shows me that when I look at the green bars, I am looking at the observations within a group minus that group's mean. That will give me those green bar deviations, which I can then square and sum up over all of the groups. Over on the right, it's showing me those particular sums of squares. It reminds me of the relationship between all of those. It then moves into calculating my f-test statistic based on the mean sum of squares between and the mean sum of squares within, and I get a rather large f-test statistic. It produces a note here saying that because the group means differ significantly, the mean sum of squares between is much larger than the mean sum of squares within. My f-test statistic is much larger than 1. So the variation between groups is due to more than just random chance. And the ANOVA table below that can be expanded to show how those sums of squares are collected, their respective degrees of freedom, the mean squares that can be computed by taking the sums of squares dividing by the degrees of freedom, the f-test statistic we saw earlier, and then a p-value associated for that. Users can very quickly choose their own settings to compare. Perhaps I want to see what this looks like with all of them set equal. And playing that animation now shows right away that a very small fraction of those purple lines is going to be represented by the between sums of squares. You can see how small those red lines are now. In this case, the between sum of squares will actually be pretty small compared to the within sum of squares. And totaling those up, I see that I have sums of squares of 3, quite a bit smaller than my within sums of squares, which would be an indication that those means are closer to a grand mean. Now, if I were to take one of these and say make it 25, notice what happens. The means for group 1, 2, and 4 are still at 5. They're still in the same place, but this mean from group 3, not only is it in a different place, but it has pulled the grand mean up. And so my sums of squares between all of a sudden just got much larger for every one of those groups. They used to be very small for group 1, 2, 3, and 4, but not only are they quite a bit larger now, I'll pause it on that visual. Not only are they much larger for group 3, which we would expect because we made that larger, but because it's pulled the grand mean towards it, those sums of squares, those deviations between the group means and the overall mean have also gotten larger. This shows how some of those deviations combine to help us understand what's happening with the means of our different groups. All right, I hope you enjoyed this tutorial and I hope you enjoy this web app.